We talked about how we did this whole case study, closure conversion, type closure conversion using a cross-language logical relation. Right? And I sort of ended the lecture by saying, all right, now you prove that if ES compiles to ET, then ES is logically related to ET. Right? Okay, that effectively becomes the fundamental property for that logical relation. So today, let's go back to what I started yesterday's lecture with, right? So I motivated this by saying, all right, we want to go beyond whole program compilation, but I also said that what we want is, we want our compiler correctness theorem to allow us to link with arbitrary code, right? That ET prime that I kept putting up on my slides, arbitrary code that may have been produced by a completely different compiler, may have been compiled from a different source language, right? That was the goal. So let's see this exercise that we did yesterday using a cross-language logical relation to prove compiler correctness. Let's take a look at what this compiler correctness theorem gives us, if it actually gives us what we were after. Okay? All right. So this was the issue. So now we have a cross-language relation, and as you can see, the title says problem 1. There is a problem. What we showed yesterday, this is abstract, but we showed it for type closure conversion, is that when you have a source component ES and it compiles to ET, then we can prove a theorem like this. And again, I've written this in a slightly more simplified style, just like I had on the slides yesterday. All right, so that's what we have. This is our compiler correctness theorem. Let's see if we can use it to link with an arbitrary ET prime that someone gives me. Okay? So someone's giving me this target level code. And imagine, for realistic compilers, the target language is assembly, right? Or it's something pretty low level. It might be LLVMIR. Right? Okay, so here's the question. Does the compiler correctness theorem permit linking with ET prime? No? Okay, let's see why. So here's a sort of, I should have written this. So here's roughly what our cross-language logical relation is giving us, right? Like the definition. I'm being a little imprecise here. I should have really said VS prime. VS prime and VT prime, that should be a T. So basically what that logical relation is saying is that if you think of these as functions for a second, I'm abstracting, but if you think of these guys as functions that are waiting for inputs or something, right? There's an X that's free, and basically we're going to substitute something of type ET prime into both of these programs, right? On one side it has to be of type tau prime. On the other side it has to be something of type translation of tau prime, right? What the logical relation, if we kind of sift through the definition again, is giving us is basically saying that if you give me two components, a source level ES prime of type tau prime, my input, and a target level ET prime, this guy that I want to link with, and they're logically related, then I can plug those in to those free variables X, and I'm going to get whole programs that are logically related at the type tau. So in other words, you have to come up with an ES prime. You have to come up with it. All someone else gave you to link with is this ET prime, but you have to come up with an ES prime in your source language S. But if ET prime was compiled from some other language, it's going to be a little hard, right? Plus, in addition to that, you have to show that this ES prime is equivalent to this arbitrary ET prime that someone gave you to link with. You have to show that equivalence. Only then do you know that you are allowed to do this linking. That's because the compiler correctness theorem is effectively drawing a little boundary, right? It's saying, what are the things that are okay to link with? Like, basically, it's saying the only things that are okay to link with are things, when you can establish this relationship between an input source component and an input target component. So basically, this is a problem, right? You need to come up with this ES prime, which is not feasible in practice, right? And you can't link with ET primes whose behavior cannot be expressed in your source language. Now, this is a great moment to have a conversation about this. Okay, so what do you think? Yes? Reverse engineering. So it seems utterly nonsense, right? Like, yeah, you can't decompile a code that someone else gave you, right? So it seems bad. Anyone want to argue that it's not so bad? Yes?
Currently, your types are a specification language.
The types are a specification language. Mm-hmm.
That's what is going on here.
Yes, yes, yes.
Now, when you have an external component,
Yeah.
the component wouldn't be quite useful if it didn't have our issue is the specification language that we're enforcing on all of our programs.
Well, no, not really, because even if you don't have a specification language, suppose I don't have a specification language. In other words, I can plug in anything for my blue X or my purple X, and I don't need to specify that it needs to have type tau prime. I really don't, okay? In fact, then the situation gets worse. Now imagine that we had set up a logical relation or something in order to do this compositional compiler correctness proof, and now someone gives me an ET prime. I can't even type check it, so I don't even know that it satisfies my specification that it has type tau prime plus. Okay? So imagine that my target language is untyped. This is actually a great question. Imagine that my target language is untyped, and now someone gives me an ET prime, and I'm asking you, does your compiler correctness theorem allow you to link with this? And you could say yes. Sure, the compiler correctness theorem again says, you have to cough up an ES prime. You have to show that it's related to this ET prime. There's no specification to guide us. I don't know. I think that's a little worse, but I'm not sure. But nonetheless, the situation still stands, right? You got to cough up an ES prime. You got to prove that it's in this logical equivalence with this arbitrary code that someone gave you before you can proceed, before you can have any confidence in the fact that you have not stepped outside this boundary that the compiler correctness theorem is drawing for us, right? Basically, the real big message I want you to get out of this is that every theorem, but in this case, our compiler correctness theorem, every theorem draws a boundary. It says, under these assumptions, you get these things, right? Here, the assumption is really strong. It's asking you for a lot. In practical terms, it's asking you to take this arbitrary ET prime, and I'm going to keep repeating the sentence. You get the message, right? You can't come up with source code if your goal really is to compile with this target code ET prime that comes from arbitrary other languages. Okay? So this is not a great way to build multi-language do compiler correctness for multi-language software, so to speak. Okay. So there's another problem with this cross-language logical relation approach. Compilers are always built in multiple passes, right? So imagine that I have a source language S, I compile to some intermediate language I, and then I compile to my target language T. I would like to prove that my compiler is correct on a pass-by-pass basis. So in other words, for the very first pass, I will prove that if ES compiles to EI, then these are logically equivalent. So I'll set that up in just the right way. You could imagine that this is the target of closure conversion, so we do what we did yesterday. And then I have my next pass, EI compiles to ET. Let's say we're going lower level, heap allocation or something in the compiler or assembly. And then I show that for that pass, that the original code is equivalent to the compiled code, logically equivalent to the compiled code. Okay, so I have these two things proved. But really what I'm interested in is the correctness of the entire compiler. I want my theorem at the end of the day to tell me that if ES compiles to ET, going through multiple passes, fine, then ES is logically equivalent to ET. After I've proved this and this, can I show that? No, right? You can't, because that's a completely different logical relation. It has S sitting on one side, T sitting on the other, and these are different. And now there's different things in the literature you have to sort of look more carefully as to whether you can prove this or not. For cross-language logical relations, especially when you have state, you cannot, even if you do all the work of defining a new ST logical equivalence, first of all, you have to do that, right? Because it's different from the other two. 1 second. You first have to define this, and then you have to show that this plus this implies that, okay? And that's hard to do, especially when you have state. Now, recently there's been this work on the Pilsner compiler, which uses parametric inter-language simulations. Okay? Yesterday I mentioned this. Inter-language means cross-language again. And they're simulations. They're not the vanilla kind of logical relations like the step index logical relations that I've been showing you. And the reason that they did this Pils work is they wanted to be able to prove this theorem. Okay? But if you go look at the Pilsner paper, you'll see that proving precisely this transitivity result was one of the biggest efforts in that. I mean, they set up things very nicely, like they're sort of language independent for various passes, but proving transitivity is still an enormous task. Okay? Yes, now I'll take the question.
I would expect transitivity to work for this logical relation. So it's just a method that it's very hard to show it for concrete.
Yes, and actually, if these were genuine, if these were not, but these step indexed logical relations for mutable state, they actually don't compose. you absolutely can't do this. Like, we don't know how to do the proofs. Okay? And that's why these guys invented pills, which are sort of a cross between these step-index logical relations and bisimulation approach, right? They're sort of a hybrid. And so they're able to do this transitivity thing, but it's still a lot of work. And I mean, ultimately, it's because this logical equivalence is a third equivalence, right? And you have to show that these others are defined in a way so that you can put them together and get that transitivity. Another question? Yeah?
So can't you define the logical relation like there exists in ES such that ES is equal to?
That's a great question. And students especially, have asked me that time and time again. I'll give you an intuitive answer because I can't answer it in depth. The question is, if I understand it right, he's saying this third relation, ES related to ET, why can't we define it as follows? There exists an EI such that ES is related to EI and EI is related to ET. Okay? The problem is that there doesn't always exist an EI. Because if you think about what we're trying to really say, this is just our compiler's pipeline, right? I'm asking us to imagine that we're going to link with some ET prime, okay? So for that ET prime, you'll have to kind of go through, and I have to like wade into the technical details of the proof to show you that it doesn't happen. Anyway, so let's talk more about that one offline, because it's a rather subtle question, but between most of us logical relations and compiler correctness experts, we don't think that we don't believe that works. Okay? I have a conjecture as to when that can work, but that's a completely open research problem. So, for another day. All right. Okay, so let's talk about why transitivity for logical relations is normally easy. Imagine that you have a single language and you set up, let's say, a step-index logical relation for that single language. Okay? So in that single language, this is a single language logical relation now, all right? when E1 is related to E2 and E2 is related to E3, how do we prove transitivity? And the truth is that even there it's a lot of work. I've only proved it once in my entire career of doing logical relations, right? My very first binary logical relation paper, because I just wanted to see how it happens. Normally we don't actually go through and carry out the proof directly. We argue it like this. We prove that the logical relation is sound and complete with respect to contextual equivalence, right? This is a language. We're defining a logical relation for equivalence, right? So we say that we prove that it's sound and complete with respect to contextual equivalence, right? And it's trivial to prove that contextual equivalence is transitive. Utterly trivial. You could do the proof right now in like 3 minutes or 2 minutes. Okay, so from that, since contextual equivalence is transitive, the logical relation is transitive. That's how transitivity falls out normally. Okay, this is sort of an established practice. But now going back here, you can't use this idea here because we're saying the logical relation is sound and complete with respect to contextual equivalence for that single language. Now, this logical relation is between two different languages. There is no definition of contextual equivalence for a language that you can appeal to, right? We set up this logical cross-language relation yesterday, and then we proved that when ES compiles to ET, ES is logically equivalent to ET in the cross-language relation. There was I never got to anything after that saying, contextual equivalence, sound and complete, the way that I had done the day before, right? Anyway, okay, so the single language trick doesn't work here. So yeah, this is a cross-language relation. There's no definition of contextual equivalence we can appeal to. All right. So basically what we need is a new approach. And we need something that works for multipath compilers and that allows linking with target code that comes from anywhere. Okay? So now what I'm going to show you is work that, is an approach that my group has been doing for the last couple of years. But, I'll admit to you up front, we're in the very, very early days. We honestly do not know if even this approach scales to realistic compilers. All right? But what you're going to see is another way of using logical relations with another idea, but this time to prove compiler correctness theorems that do allow both multipath compilers and linking with arbitrary code. Okay? So let's go on. All right, so back to the original question. How do we express that equivalence given our goals of multipath and linking with arbitrary code? So there's our arbitrary code again. What we really want, morally speaking, is to be able to say that when you link ET with ET prime, and you run that program, you get the same behavior as when you link ES with ET prime. Right? Wouldn't it be nice if we could say that? When we link ET with ET prime and we run this program, we get the same observable behavior as when we link our original program with ET prime. Because that would mean that these two put together are the same as these two put together, right? Yeah?
What would it mean to link ES with ET prime?
Here you go. Okay. Exactly. What would it mean to link ES with ET prime? It doesn't mean anything. We don't know how to link source code and target code. So what we need, if we want to formally specify what such linking could possibly mean, we need to specify a semantics of source and target interoperability. Okay? Multi-language semantics exist. Semantics that, boundary, okay, so let me just explain what this is. So I'm asking you to imagine a source target in multi-language semantics that takes the source language and the target language and puts them together. And in the multi-language, it adds one new construct, two new constructs, two new boundaries. This boundary, when I put this boundary around a source component, it lets me take this code and put it inside an arbitrary piece of target code. And then I'll define operational semantics for the boundaries later, okay? This boundary lets me take an arbitrary target component and put it into, when I wrap it, I can put it into an arbitrary source context. So now you can take target code and effectively be running it in source context, and you can take source code and be running it in target context. So you have interoperability. So that's kind of what I mean by linking. And in particular, then, if you had such a multi-language semantics, which needs to have all sorts of properties, which we'll get into, if you had such a multi-language semantics, then basically what you want to fall out of your compiler correctness theorem is that when ET is linked with ET prime, and you run this program, you get the same observable behavior as when ES is linked with this wrapped, ST-wrapped ET prime. Okay? So it's a way of wrapping and embedding this target code into my source code, but in a sensible manner, which we'll see. Yes?
So you said earlier that it would be hard to reverse engineer a source, a target language program.
Yeah.
One rather stupid suggestion is if you just take everything in the target language and add to the source language,
yes. Yes.
Right? But
And that's,
don't use those features. Is that what we're doing?
yes, kind of. Exactly. Because I want to be able to run, so see, I've just embedded this ET prime into my source language, but when I actually go run this full program, what's going to happen is that I'm going to run this little component using my target language semantics, and only when I get to a value form, I'll know how to convert it. I'll tell you, using my new operational semantics extensions, I'll tell you how to convert a value from this target language to give it to the source.
So you do need a translation layer.
You need a translation layer, yeah. We'll see, yep. Okay. So if you can do this, then here's basically what you can get. And I've already said this. ET linked with ET prime, I just sort of write it as application, right? But this means linking, is the same as ES linked with this wrapped thing. But now this is on a target language thing, and so I have to put a TS boundary around it so that I can make the other side a target language thing as well. Okay? Because this language is a multi-language, but when you say contextually equivalent, you have to either be on the purple side or the blue side. Okay? So that's why there's this extra TS around it to take this blue thing and effectively allow you to put it in a purple context because there's purple on the other side. Good? Okay. All right. Then this ES equivalent to ET that I've been asking all along, how do we define this? We can define it simply by saying that the original ES that we're compiling must be contextually equivalent to the code that we've produced, that our compilers produce, but with an ST wrapper around it. An S3 boundary wrapped around it. Okay? So this multi-language is a more powerful mechanism. It's letting you express. I mean, in some ways, I kind of motivated this with the transitivity issue, right? I said, in a single language, you have a definition of contextual equivalence. And you can just say my logical relation is equivalent to contextual equivalence, and transitivity falls out for free, right? I've taken both my source and target languages, and I've embedded it into a multi-language, and now it has a definition of contextual equivalence. And transitivity will fall out for free. Okay? So we'll see. Actually, I think I've said what I was about to say. So if you have an SINT multi-language, SINT multipath compiler, then what the multi-language approach advocates is that you have to define a multi-language into which you embed all of these intermediate languages. And basically, the idea is to go kind of pass by pass. So you define this SI and IS boundaries, which let you mediate between these two, and you define IT and TI boundaries, which let you embed, purple into orange and orange into purple, right? So you're doing this on a pass-by-pass basis for the compiler. And then what you can do is compiler correctness. For this pass, when you compile ES to EI, you prove that ES is contextually equivalent in the language SIT to, EI wrapped. And similarly, you do that for the next pass. All right? And now let's see whether we get transitivity. So if I have proved for this pass that ES is equivalent to the wrapped EI, and for this pass I've proved EI is equivalent to the wrapped IT, I can simply put an SI boundary outside this guy. And that would mean that I have to, similarly put an SI boundary outside this guy. So if we put two SI boundaries around both of those bottom things, like that, what do we get? ES is contextually equivalent to SI, which is contextually equivalent to SIT. And we get the final compiler correctness theorem that we are actually interested in. The SIT here is an abbreviation for SI of IT. Okay? I'm just saying that these boundaries, you can keep, sort of layering them on top, and they compose. Okay? All right. Yes?
So, can't we directly go from source to target when we're doing contextual equivalence? Because, we're first translating from X to Y and then from Y to Z.
Mm-hmm.
When we're just doing the translation, can we don't go directly from X to Z? Is it necessary to go to Y?
Oh, actually, it's precisely when you're doing the translation. If by translation you mean compiler. Yeah. But you really want to write your compiler in multiple passes. Like, that's a given. Any realistic, full-featured, whatever, like optimizing compiler, especially for high-level languages, they cannot be implemented in a single pass. People write little papers in which they show that they can do this in a single pass, but that's never going to be a realistic compiler. So I think it's a given that we want to implement our compilers for realistic languages in multiple passes. It just makes it much easier. Otherwise you're going from, imagine, ML to assembly in one pass. You just can't do it and get it right in some sense. It's too tedious. Yeah. Yes, so I haven't said anything about what types are on the two sides of the boundaries, but that's what your question's about. Okay, so hold off for just a minute or two. All right, so I talked about how it fixes the transitivity problem, and we've already sort of talked about this, how it fixes this problem, right? We don't need to cough up an ES prime when someone gives us an ET prime to link with. We just take that component. You don't have anything else, right? This is all you have, the thing that you're going to link with. But if you put it under a boundary, you know how to make sense of this, right? You know that you can link with it. And then you get, we've already seen that. Okay. I'll get to your types thing in 1 minute, okay? All right. So what we've been working on in order to see if this idea even makes sense is a compiler from System F with recursive types. And recently we've added mutable references to the source as well. So it's ML, basically. And we do this multipass compiler. It's very much along the lines of the System F to typed assembly language paper that I mentioned to you guys yesterday. Except that paper also does CPS translation along the way, and we don't. Minor difference. But okay. And we go down to a typed assembly language. So we do closure conversion. These things are meant to indicate type translation. So you take an F type and you do a C translation to get to the C language. You take a C type and you translate it. So yesterday I was writing plus. Now I have multiple languages. I have to write letters. That's all. Okay? And you, for every pass, you do a type preserving translation. Okay? Down to typed assembly language. And then what we do is we define these boundaries, right? So here's where the types are. Okay? I hadn't mentioned this before, but these boundaries, they always mediate between something that is a type tau on one side, and what you get out of this wrapped thing will be something of translation type, tau plus. So this boundary mediates, these two boundaries mediate between tau and tau C translations, right, to the next layer. These boundaries mediate between the orange type and its translation, and these boundaries mediate between the next two, okay? So always the target code has type tau plus, and on the source side you have type tau, okay? And then when you flip, inside you put something of type tau, and on the outside you get something of type tau plus, okay? And this, now back to your question, I don't know if you want to sort of ask it again, or does that answer it? Yeah. Okay. So basically, what he was, what you were saying was that, you know, it's these type translations that are kind of enforcing a certain calling convention, a certain protocol. I'm not putting just any arbitrary junk under this boundary. The tau plus is going to guide me a little bit in terms of making sure that at least what I get from that side that I have to convert over to the source side is somewhat sensible. So if I expect an integer on the source side, at least I'm getting an integer on that side. If I expect a function on the source side, I better have a closure, in our case yesterday, right? Something of a type exists, alpha, et cetera. That closure type on the other side. Otherwise, it doesn't make sense to do these conversions. Yes?
Just to install, like, for example, from going to F to C, we define C as part of the system observation between source and time.
Yes.
So just going from C to F, is just a reverse relation, and do we just translate back to the top?
No. This is going to be a multi-language semantics in which these boundaries are going to be given operational semantics. So here we go. Okay? And we'll actually go through the case study of closure conversion all over again and do that. But it's not a translation. It's not a compiler. These boundaries are not compiling from one side to another. And you'll see how that sort of manifests itself when you start going through the exercise of writing down this multi-language semantics. Okay? But at a high level, what we want is that if we have some, you know, CF with a source thing underneath it, again, I've said this already, I want to run this blue expression using the operational semantics of the blue language, get it down to some value, and then all the boundary knows how to do, effectively, is to convert it into an orange value of the type tau plus, tau C in this case, okay? And vice versa, all right? So this has type tau plus, translation type. We run it using the orange language's operational semantics till we get to a value found, and then we convert it over to the other language, right? That's the high-level picture of how we're going to set this up. So really the most interesting part then is, depending on whatever this type is, how does this boundary conversion happen? And I can give you a hint. If this is a number, 5, I'm going to produce an orange 5 on the other side, okay? If this is a function, I'm going to produce a closure on the other side, all right? Okay, and we'll do that in a second. Yes?
All this missing piece in translation business, can't we really think of them as a package of an existing exercise? Because we're kind of providing an interface between the two languages which just needs to be used.
So you're thinking of the boundaries as some sort of interface?
Yes.
The boundaries are very much an interface, but I don't know what you mean by existential type in that context.
I mean, can't we just say that we require each of the pieces to provide an interface of an existential type which can be used as one operand?
I'm not entirely sure how that would work, because one of the things that I want you to sort of take away from this is that one thing that we're trying to do with the multi-language semantics is we're trying to make sure that these languages are embedded into the multi-language in a faithful fashion, as in they are genuinely embeddings. It's not that, you know, when you take the source and the target and you embed it into the multi-language, that if you run a purely source component in the multi-language, it better run exactly the same way as when you're running it in the source. Same for target, okay? And that has to do with the fact that this multi-language system is something that we are defining in order to write down our compiler correctness specification. Just like yesterday, how did we write down our specification, that equivalent specification, in order to specify when ESs are equivalent to ETs? We did it by writing down that cross-language logical relation, right? Today, I'm asking us to write it down in a very different way, and I claim that this gives you a more powerful theorem. That's why we're doing more work, okay? So now I'm asking you to write down the specification by defining a multi-language system that is sensible in various ways. And let's talk about one of the properties in which it's sensible. So one of them is this, that it has to be an embedding. Running a purely blue thing in the multi-language alone should be, you know, it should run exactly as if it runs in the blue language. And another one is boundary cancellation. This is really important. If I put you know, 2 reverse boundaries around a component, I should get something that is contextually equivalent in my multi-language to the original component. And if I don't get this property, boundary cancellation, falling out of the definition of contextual equivalence for my language, then I haven't defined my multi-language properly, and it shouldn't you know, there's something wrong with it. You can't use it as a compiler correctness specification. All right? Okay. All right. So if you, yeah. Oh, sorry. Yes.
So what happens if my lowest level language like writes to a random memory address or some kind of side effect like that? Does the typed assembly language prevent me from writing programs that do nasty things?
That do what kinds of things? Say that again.
So say I write to a random memory address that is being used in some of the higher level code.
Oh, yes, I
As a side
would.
effect in my assembly code.
Okay, yes. So part of the work that we've been doing, we've been very obsessed with compiling high-level typed languages, and in particular with type-safe interoperability with the assembly. So we have actually designed our typed assembly language, multi-language system in a way so that we don't allow it to clobber certain things. Okay, it's in the spirit of the original typed assembly language, which was also type-safe.
Okay.
So it would prevent.
You've carefully designed the type assembly language.
To ensure type-safe linking, yes. But there's a sort of longer-term question here. Ultimately, we'd like not just to be able to link with typed assembly language, we'd like to be able to link with code that's compiled in untyped or dynamically typed languages as well, and how do we deal with that? And right now, there's a conjecture on the table, which is that you can read more about this in my Snapple 15 paper, where I sort of lay this out. But maybe we can use things like sound gradual typing to achieve that, if any one of you knows what that is. Otherwise, we'll get back to that later. Okay? Yes? Yes, we'll call that the bridge lemma. You'll see. We'll get to it by the end. Okay. Yes, very good point. Yes, sorry.
Does this also require that from like F, C, A, and G, that T has sort of express fewer values than your higher level languages? Because, for instance, the semantics you written on the board, how would you translate your pack in your lower level semantics up into the value?
We'll see. I'll show you. We're going to do that on the board. Okay? All right. Okay, so if you want to read more about this, there's a paper which talks about the first two passes. The last pass we are working on, we have actually defined a multi-language between the TAL and a higher level functional language, and we have the fundamental property proved, soundness and stuff with contextual equivalence, but we haven't yet used that logical relation to do the compiler correctness proof, but I think that's the least of the problem. The problem was always multi-language. Anyway, okay, so let's do this on the board. Let's go back to our case study and see how we would define a multi-language semantics in order to do that same compiler correctness proof. But this time we get a stronger theorem, right? Okay. And I hope it's clear, right? Like even if I guess this is a good segue point. In general, it's kind of clear that TAL can have lots of features. Assembly has lots of features. Like let's say, in assembly you can jump all over the place, right? Control flow-wise, it has bizarre behavior compared to a high-level language. So that's kind of problematic, right? Like if your target component has these features, even if it's just sort of using them internally, it's not clear that you can express that in a source language, right? So this idea of taking an ET prime and coming up with an ES prime is really sort of, you can't do it in a lot of situations. Other examples are, suppose that I'm writing code in a functional language and there's no state, but my target language has state because I'm compiling a different language which has mutable references down to that same target. Right? So now the target has to have state because it needs to serve as a target for two different compilers. So it has to be richer than the language that I'm compiling to it, right? Which is purely functional, let's say. So in this situation, what do you want to link with is a really deep and important question, and it's sort of, I don't know, you can give multiple answers to it. You might say that I never want to link with code. So let's take the example of higher order functions. I'm writing code in a purely functional language, and I need to take as input effectively an int arrow int function. All right? This int arrow int function now is going to be given to me through my target language, and that language has state. So if that int arrow int function can internally manipulate state, then I'm linking with some code that I can never write in my source. Is that okay? Do you want that? How many people would want that? Yeah, some people would. It actually is kind of a good property. Like if your source language is Coq, for example, you're writing Galena code, it's pure. If you start linking with stateful stuff, what does that mean for all the stuff that you proved correct in Coq, right? So I claim that if you're doing something like that and your source is Galena, you really don't want to link with that stateful code. So maybe you can use a type system at the target to say, a modal type system to say that, to keep stateful computations separate from the pure ones. And then you can devise your type translation so that you write your compiler in a way so that you say, I'm only going to link with code that is pure. All right? But another thing is, there are other programmers who really might want to link with code that can do stateful stuff. I can't do stateful stuff in my language, it's impoverished, but I want to link with all that other code, you know, and actually pull in some imperative modules because I can write them more efficiently. And that's another use case. For that, you would devise a different, if you take this type translation point of view, for that you would devise a different type translation, right? I'm sort of saying all this because I feel like there's this space to be explored in language interoperability. Our language specifications are not complete in the sense that we don't allow programmers to specify what it is that they can link, that they want to link with. And I've just given you two scenarios where I think that both those programmers would want to link with different things. So maybe there's like a lot of research to be done in language interoperability and sort of linking, right? So that we can give source programmers the ability to say, what do I want to, feature-wise, what do I want to pull in from another language? What am I okay linking with? Because this impacts how you reason about code in your own language. In one scenario, you can reason as if you are always going to link with pure code. That means you can reason in a pure fashion. Certain equivalences hold. Certain optimizations hold. But if you want to link with stateful code, then those equivalences no longer hold, right? And then you can't just sit there and reason as if you are programming in a purely functional language without being aware of the fact that you're going to link with stateful code. Because, right, your reasoning has to be different. Correctness is different. Not the same things are, certain equivalences no longer hold. You have your hand up, yes?
So my question starts from the observation that currently we're defining our language wrapping in the way that we get the target language module, that we wrap it with the boundary, and then we get the source language.
Yes.
What if we looked at what if we took our source language module, wrapped it with the boundary, we get a target language module? In that case, if the target language is less restrictive, we would have mutable references there.
The target language is less restrictive. Yeah, sure, yeah. So you're saying take your source thing and wrap it and put it in the target. Yeah, okay. The problem is you need to be able to go both ways, and it has to do with functions. Because functions contravariant argument, I'm imagining that I'm compiling a language with higher order functions, okay? This is in the ML sort of space. If you only care about first order, then maybe that situation doesn't arise, but I haven't thought about it, okay? But otherwise you need to go both ways, sadly. That's why this multi-language semantics has two boundaries and it goes both ways. And you'll see this actually in a few minutes, okay? Let's grab chalk. All right. So our first task is to take our source blue language and our target red language and get some white chalk so we can do a multi-language. Okay. What I want, I'm going to use white for when terms are in the multi-language. Okay, so terms in my multi-language, I'll use phi for types in the multi-language. Okay, so the grammar of types in the multi-language is really pretty simple. A multi-language type can either be a blue type or a red type. Okay? If we look at value forms in the white language, same thing. Values can be blue values or they can be red values. And you'll see how this picture emerges, but bear with me for a second. The most important thing, though, that we want to do is add boundaries, right? But boundaries are expressions. They're not value forms, right? Because I was saying that when you have boundary wrapped around a value, you convert it to a value in the other color, right? So basically, we want to take, now I'm going to essentially take this grammar and start treating it as a multi-language grammar. And what I'm after is something like, I want to say expressions in my multi-language can be either blue or they can be red, okay? But now let's go over here and add our boundaries. So here I want to add, I'm going to go a little crazy switching between colors. So I'm just going to write ST in blue, okay? ST of E, okay? and this is going to be, I'm always going to put the source type on this side. So this means that E must have type tau plus, then ST of E has type tau. Okay? All right. For the expressions which are on the bottom line, unfortunately, we're going to add a TS boundary. And under the TS boundary, we can put arbitrary source expressions E, and these will have a source type. I'll put it on that source side. But again, the other side has a type tau plus. Right? Okay? What else do we need to do? Let's be precise about evaluation context. Yesterday I didn't write any down. I just sort of told you the operational semantics for this language is standard call by value. Same thing for this. So I'm going to trust that you understand, that you know like what the blue evaluation contexts E should look like. Basically normal, but it's a blue hole. Let me point that out at least. Okay. And then the rest is normal. And for the red language, when we have evaluation contexts, I guess I'll put it here. We have a red hole target, okay? And then the rest is what it would be for the normal language. Okay, so far, that's from yesterday. But now I want to extend these evaluation contexts for the multi-language, right? So I want to do the same exercise, and I want to say multi-language evaluation context means you are either evaluating in using the blue or you're evaluating using the red. Okay? But that means that I still have to talk about, hey, when you see a boundary and there's an expression here, you have to evaluate this down to a value, right? So that means that we need an ST boundary which says, go use red evaluation rules to evaluate in this position. Okay? That's how we're going to get our red E down to a value. And similarly over here, we need to say TS of blue E. Okay? Good? So far, like with the evaluation context, it's nothing more than what I said before. If you have a red E under a boundary, you need to reuse the red semantics to get it down to a red value, and then we'll give you boundary reduction rules, which we're about to do next. Yes? Say that again? I motivated the boundaries as mappings between... that's... Okay, so let's write that part down. That was what I meant by... those are going to be primitive reductions. So when we take... let me get to the operational semantics in just 1 minute because I want to show you the typing rules first. I'm going to put the typing rules here, I think. Yeah, because I'm running out of space. So remember that we only have type variables in this language, red alphas, right? Remember we were type checking this with a red delta yesterday? Red delta, red gamma, E colon tau. Okay, and this we were type checking blue gamma, blue E colon tau. All right, we're gonna pull all of those typing judgments for both of those languages into our multi-language. One thing that's going to happen is that for all of those blue typing rules, you're going to have to put a dot in the delta context, because in our multi-language, we have type variables because our target language is bringing them in. Okay? So our multi-language type judgment is going to be of the form, well, technically you could say it's of the form delta gamma E colon tau, right? But let's sort of dive down a little bit deeper. This delta will always be red. It will only contain red alphas because there are no blue type variables. All right, so I'm just going to do that right now. Okay? But this gamma, it needs to have variables from both languages. So what we need to do for that is we need to define, let's extend the grammar here. Gamma is going to be either empty, or it's going to be the multi-language gamma with a blue variable with a blue type, or it's going to be a multi-language gamma with a red variable with what type do you think? Red tau? Blue tau plus. Okay? This has to do with the fact that I don't ever want to really deal with inputs that aren't of translation type. I don't want to link with components that are not of translation type. Okay? And remember, these variables are positions where you can come plop in a component that you want to link with. So this says you can only link with components that are of translation types. So there's some sort of sensible, convention that they're following, some sensible specification that they're following. Okay? All right, so if that is my gamma, then I need to just add 2 typing rules. I keep putting the chalk on the other side. I need to add 2 typing rules for my boundaries. All right. Again, white delta or red, doesn't matter. We are going to have a boundary for ST. So this thing has a blue type, this one, tau, if under delta gamma, E has type translation type. Right? And vice versa. TS of blue expression with a tau here has type tau plus if under delta gamma my blue E has type tau. This is hard to write switching colors 3 times. Okay, but I hope it helps see what's happening. All right, so now let's go and write down those boundary rules that are really the most interesting part of this whole exercise. I'm sorry, I'm going to erase the gammas. Okay, so the boundary semantics are defined in a type-directed fashion. So for every type in the source, we're going to have 1 reduction rule. So in particular, let's say we take ST with int on the outside, and inside we have this red n. Right? Remember from yesterday, translation of blue int is red int? So this is going to step to, what is it going to step to? Blue n. Right, and vice versa, right? Okay. Now the other one is the more interesting one. When we have ST of tau 1 arrow tau 2, and I'm just going to put a v here, a value, but let's think about what type that value is going to have. It's going to have type translation of tau 1 arrow tau 2, right? Does everyone remember the translation from yesterday? Should I write it down? I'll put it here for reference. Sorry, it's dark. A tau 1 arrow tau 2 plus is exists alpha. Yep. Oh, it's running into that. Tau 2 plus, comma what? Right. So it's this whole thing paired with an alpha. This should be an angle bracket. Okay? All right. I really wish we had our whiteboard from yesterday. Okay. So this value has that existential type, right? In other words, what form is the value? What kind of value is it? It's a pack. Okay. So it's a pack. So what are we going to do with our pack? What do we want to produce on this side? That's the first question to ask. What kind of blue value do we want to produce? A lambda. Okay. I'm going to start with that. We're going to produce a lambda that takes a tau 1, in fact. Okay? And then in the body over here, we want to produce something that is a blue tau 2. Okay? All right, only we want to use this guy to produce it, so to speak. Okay? Okay, so how are we going to do that? Well, so since we can take this function, this pack, v, and we can unpack it, right? So let me sort of start doing that right here. Unpack, oh, there's no space. Okay, let's try it. Alpha, y. I'm going to unpack this pack, v, and then do something with it. What do I want to do with it? Yeah. Take the first projection of y, apply it to the second projection of y together with the input to the function. What's the input to the function? TS. I can do a TS to this x that I have sitting out here. So what am I doing? I'm taking my input x, I'm converting it over to target code, to target land, giving it to my target function, which is this projected y. The function is computing an answer for me. So basically this whole code here is producing something of what type? Tau 2 plus. So what are we going to do in order to get a tau 2? ST. Right? Yes, the other way. Okay, so this is partly an answer to the question of why do we need boundaries in both directions, right? Functions show you, this is, those of you who are familiar with higher order contracts, for instance, this is the same sort of idea. Whenever you get to higher order functions, which is what these are, you have to go both ways. So because function arguments are contravariant, here we take the input, we convert it to target land, we take the answer, and we convert it to source land. Okay? Now, let's do more. Where should I write? It's an honest question. Tell me where. Should I erase what I just wrote? Or should I erase some of this? Yeah, we'll get rid of this.
Are you relying on the fact that the new tau to the right of it can't have the existential type in it? So you never check these where you are stuck with having to translate a pack that does not represent a closure?
Yes. Yes.
So you never end up in a case where you have to turn just a pack that's whatever,
I
not
never
necessarily a closure, into a
precisely.
blue tau.
Precisely. So this is a very, very important point. My boundaries mediate only between taus and tau pluses. That's why the first question I asked you was, what is the type of V? It has to be of type tau 1 or tau 2, and that is the thing that ensures that this V is not just any existential, it is an existential with this shape. It has two things inside the package, right? It has this function, and it has an environment. And that function then takes exactly that environment as its first input, etc. Right? So that type translation is what lets us actually do this, right, in a sensible manner, without getting stuck. Otherwise, and in fact, you get a type safety result for the multi-language semantics because you've set things up in a type safe interoperability kind of way. Yes? It's not. It's not just the image. You can, what's really cool about this is that you can, so you see this function V, this package V which has inside it a function. It doesn't have to be something your compiler produced, and that's the cool thing. Inside that function, you can be using extra features which your compiler could never have produced. For example, remember I threw in polymorphism into the language yesterday. I could throw in some more stuff. I can throw in exceptions. And now this function that's sitting inside my target package, the red package, that function internally can be using any of these red language features as long as by the time that function has computed, the thing that it gives you back is a tau 2 plus. So that's why this is so expressive. Because you genuinely now have the ability to take target level features and pull them into the source even when the source didn't have them. The type. So this ET prime that you link with, it has to have a translation type, yes. If it does not have a internally, it can use all sorts of target features that do not exist in the source. But after you type check it, the resulting type has to be a tau plus. That's the restriction. So it's sort of extensional. We don't care what you do on the inside. We only care about what you return, because those return points are your interfaces, right? If we can make sure that your inputs are all of translation type and your outputs are all of translation type, that's what we care about. It gives us sensible interoperability. Okay? That's why the inputs matter, right? Remember those red X's that we put in our gamma? They have translation type because those are input points. So we make sure that we only have translation type inputs and translation type outputs. Okay. Erasing. All right, so our next step is to, write down the boundary rules in the other direction. This is a little hard to erase completely, so. All right. So the TS rules. TS. TS of a blue V that has type int. What do we produce? I guess I should write n. N. It steps to a red n. Okay, and then the interesting case. TS of a tau 1 or tau 2. Now, same exercise again. This is a function. I'm not writing it out as a lambda, but that's what it's going to be. It's a function of type tau 1 or tau 2. By the way, I'm saying that this is going to be a lambda, right? A blue lambda. But on the inside, you know that it can have many boundaries, and it can have red code sitting deep in the body of the lambda. Yeah? Just want to make that clear. Okay? So it's a blue lambda with a body that returns something blue, but on the inside, it can have an ST boundary and some red code sitting in the middle, as long as what it returns overall is blue. Okay? So this is genuinely mixed. All right. So what we want to produce this time has this existential type. We want to produce something red that is of this existential type. So we'll produce a pack, right? Now, pay attention. My pack needs to have a witness type. Witness type for the environment, right? What is alpha going to be is our first question. Other than that, we know that when we create the pack after we've picked our witness type, we need to put two things in it. We need to build one of these functions to put in, okay? And then we need to put something of the right witness type. I think that's how we're going to assemble this. So the first decision is, what do we put in the environment? What is the witness type? The free variables of V. Good. What are the free variables of V? Who said that? Yes. None? Tell me why.
Because it's operational semantics.
Yes. The operational semantics is defined on closed terms. The free variables of this blue V are nothing. Okay? So we are going to pick the unit type, or in this case, I've been using the empty tuple type, right? This is the empty tuple type, just like we used it for something yesterday in one of the examples. Okay. So you see, I'm not compiling. This is one of those moments in this multi-language semantics where you are not writing a compiler. The boundaries are not implementing a compiler. They are implementing a runtime semantics. It needs to be sensible in and of itself. Okay? All right. Okay, so That's our witness type, and now we need to put a pair there. And our pair needs to have a function, a red function, that takes two things. Actually, let me just call that function a v, and then we'll sort of define it separately. I'm going to put a function. We'll define this in a second. We'll figure out what v needs to be equal to. And then the environment, empty. Right. OK, so what does this function have to do? Well, it has to take two things. What's the type of the first input? Right, empty. And the second one? Some red X. Look at that type. Of what type? Okay. And then what? How do we get the body? How do we get back something? Here, we obviously need to get back something that's a tau 2 plus, right? Because that's what the translation says. Remember, we haven't used our blue V yet, and we have to. Okay, so we're going to do the same back and forth thing that we did over there. Only this time, we're going to do, well, we're going to take our blue V. We need to give it as input a blue, well, an input of type tau 1. We only have an input of type tau 1 plus, so we're going to convert it. So we're going to do st tau 1 of our red X, right? That's our input. And now we take this whole thing, and this is producing a tau 2, so we're going to convert it using our TS boundary into a tau 2 plus. Okay? Same back and forth idea. Really, the interesting observation here was, your witness type for the environment is empty. Okay. All right. So that's the operational semantics. Any questions? Yes?
Can you explain again why this will always be a closed term?
Okay. When we're defining operational semantics are about running programs, and we normally define them only for closed programs because you don't run open programs. So that's why nothing will have a free variable. Like E steps to E prime, the step relation for this language, E steps to E prime, is defined for closed programs E. They have no free type variables and no free term variables. So therefore, this doesn't either. Okay, can someone help me erase? Like when I'm writing on one part of the board, can someone erase on the other side or something? It would save us time. No volunteers? Can you erase that side? I think it's time to get rid of everything. Oh. Yes.
Sure.
Commitment. Okay, so the next thing we're going to do, now that we have a multi-language, is we are going to define a logical relation for this multi-language. Actually, we could do two things. We could first write down what our compiler correctness theorem should say so that at least we have an idea. Would you like to do that first? Because that's going to be stated in terms of contextual equivalence for the language. But the thing is, you can't do proofs of contextual equivalence. So in order to prove compiler correctness, we want to use the logical relation so that we can do it easily. Okay, that's why the logical relation is going to come in. Oh, this as well. All of it. Hard to erase, isn't it? Nothing's happening. I know. It's like you keep going. A lot of exercise, but nothing happens. Okay. So right now, I think I'm just going to put down a very high-level notion of compiler correctness. I think so. Basically, we want to say that if we compile some blue E of type tau, we compile it to some red E, then what? Well, we want, roughly, and this is rough, it's not going to be correct, okay? We want the blue E to be contextually equivalent in the multi-language to the blue wrapped red E at the type blue tau. Yeah? Seem reasonable? Are people wondering why I said it's not quite correct? It's not quite correct because this judgment form right here has my original blue gamma, which has all these blue x's in it. But when I compile, remember our compiler from yesterday? Any blue x's that are sitting in here have been turned into red x's when you get this term. So you have to do this like substitution of variables. So let's write it out a little bit more, the exact form. I'll cheat a little by writing my gamma as a vector of x's, which is what it is, right? Right? But now on this side, we need to do a substitution. And basically what we need to say, and I'm sorry, I'll put it over here. We need to say that in that E, we want to substitute Ts of whatever these taus are, right? Blue tau of blue x for all the red x's. So take this and insert it right here. All it is take all those red x's that are sitting in your compiled code, but now they need to talk about the blue because that's what we have in our environment, right? So we're going to put in, we can't just put in blue x variables for red x variables directly because they don't have the right type. They have type tau. And the red x's have type tau plus. So that's why we have to wrap them in a boundary. Okay? All right. Tedious, annoying, but anyway, it's what falls out. Okay. Now, so this is the theorem we want to prove, right? And I have already said we don't like doing contextual equivalence proofs directly. It's too hard. So we're going to use a logical relation for this thing. So let's look at what shape this multi-language logical relation has, right? And this is kind of interesting how this turns out. So yesterday our logical relation was cross-language. It was relating these blue V's to these red V's, right? And today we're not defining a cross-language logical relation. We are simply defining a logical relation for the multi-language, nothing else, right? So all we need to do then is define, let's start with the value relation. I'm going to define this, let's do the blue types first. Basically, whenever we do a logical relation, what do? We define value interpretations for every single type in the language, right? Look at your notes. I know I've erased it, but what are the types in this language? Actually, it's still up here. The types in this language are this white phi, and the white phi can either be a blue tau or a red tau. Certain advantages. Okay. So that means for every single one of those types, we need to give a value relation, right? Okay, so right now I'm starting off with my first blue type. And what are the values that have this type and that I can put in here? What are the values that have blue type int? Blue ends, and that's it, right? Nothing else. Binary relation, because it's for equivalence. So there's two of these. And there we go. And by the way, this also I'm building with typed things, only I'm just not putting that on the side, right? So both of these have to have this type, and they have to be closed. All right? I can put that here if you like. V of any type. Let me just stick to a blue type for a second. If any blue type means that you are putting in values v1 and v2 such that both of these right? Vi have the type tau that's out here under a closed environment. Only now we have two environments, right? Okay, so I need another dot. All right. Similarly, when we do this for red taus, we'll have a red V1 and a red V2, which again, inside them, if they happen to be functions, they can have blue code, right? They can have code from the other color language. But they'll be on the outside, they'll be red, so to speak, for red types, and they'll have to be closed under and of that type. Okay? All right, so let's go back and do the event. You're going to find this boring, frankly. Tau 1 or tau 2. What do we put in here? What are the values that have blue type tau 1 or tau 2? What form do they have? They have to be lambdas, and they have to be blue. So lambda x colon tau 1 dot E1 and lambda x colon same tau 1 dot E2, right? And when are they related? When you give me two related inputs, what color are those inputs going to be? When you give me a V1 and a V2 that are related in the argument type, tau 1, right? Then I do the normal thing where I take the bodies of these functions, E1, stick in V1 for x, E2, stick in V2 for x, and I get related things in, just like yesterday, expression relation at what type? The result type tau 2. Okay, see, I said you would find it boring, right? But that's good. All right. Okay, so that's the two cases for our two blue types. Now we have a whole bunch of red types. That's kind of annoying. All right. Well, you know what red int is going to be, right? I can do this right here. Right? Okay. How about, what is interesting? You want to do functions? Yeah? Okay, so in the red language, our functions have the shape, they take multiple arguments. That's just a little bit different, but, not very different. So we take a vector of these taus, we'll call these tau i's, and we produce a tau prime, right? And in here, we have to have, instead of the blue lambdas, we have to have red multi-argument lambdas, so it's basically there, right? And we're going to do the same exercise. This time we need to pick a vector of these guys at those argument types tau, this one, right? And after, we put the vector over the whole thing, right? We pick a whole bunch of those, and then we substitute them into the bodies. The V1, again, I'll write this as a vector as well, right? You get the idea. Okay. All right. Good? This logical relation is actually far easier to define than the cross-language one, right? Because it's more boring. It's more standard. It's not asking you to take, to figure out how a tau relates to a tau prime, because we did that elsewhere. We did that in the specification of the multi-language semantics. It'll come up in your proofs, of course, like when you have to prove the fundamental property and you hit the typing rules for boundaries. You'll have to do a bit of work there. But in the logical relation itself, it's really simple to look at the definition. Like, it's normal. Let's do, this language also has type variables and existential types. And throughout my 3 lectures, I haven't talked about polymorphism because you guys did that with Dan, right? So this is our chance to just sort of go do that. So we need to define value relation for our type alpha, red alphas, and we need to define value relation for our existential types. So we'll do that. How do we do that? What is the interpretation of that? The relation, yes, you need a relation, right? Where does the relation come into place? So what we're going to do, and you'll see this when we get to the top level definition properly, but basically we want to be carrying around a relational substitution. I'll call it rho. In fact, the definitions that I just erased, they all need to have little rows plopped everywhere as well, even though they don't need them. Okay? They're just going to get carried around. But we need them because there's polymorphism in the target. So we need a row. Our rows are going to be mappings from alphas to triples. Tau 1, oh, they're not going to be white. They're going always, alphas are always red, so these types are always going to be red. Okay? Maybe I'll even make my relation red. There we go. Okay? So it's going to be a bunch of things like that, right? Alphas map to these triples. And this is okay, right? This is standard? We're just remembering what type tau 1 you instantiated some alpha with for your program on the left, what type tau 2 you picked for the program on the right, and the relation R needs to come from a set, rel. Rel is a relation on things of two target types, tau 1 and tau 2, and all it says is any R belongs to, is a good rel, is a good relation. If for all V1 and V2 that you find in this R, it must be the case that these V1 and V2 are closed and they have these types tau 1 and tau 2. So I'll just write VI have type tau I. Okay? Relations are nothing but relations on values of these two types, tau 1s and tau 2s, and they have to be well-typed values sitting in that R. Okay? So just like I'm sure you've done last week, in order to interpret the alpha, all we do is we pull out the relation R, right, that's sitting inside this row. So basically we want to say, go look up row of alpha, and if it's equal to tau 1, tau 2 R, then this value interpretation is equal to exactly that R. This is okay, right? You did this last week? Or is it different? It's okay. All right, good. Okay, so now let's do existential types. So exists alpha tau. What do we put in this relation? Yes?
I have a question.
Yeah.
So where are V1 and V2 coming from? They're an element of R?
Yes, R is a relation that consists of pairs of values. Okay? It's a set. R is a set that consists of pairs of values. In other words, a relation on values. Okay? But those two values that sit on the two sides in all of those pairs, they have to have the right types. Okay? The V1s all have to have type tau 1, and the V2s all have to have type tau 2. I just wrote I here because I didn't want to write it twice.
You're just saying it's some relation.
It's some relation. Any relation whatsoever, all I know about it is what types of values it contains. Okay? So in other words, whenever we write this triple, tau 1, tau 2, R, this R will always contain values of type tau 1 and tau 2. Okay, thanks. All right, so pack. I don't think you guys have done pack, actually, or existential types, right? Have you? Logical relation for existential types? No. Okay, so the canonical form of a value of existential type is a pack, right? So a pack of a tau 1 V1 as exists alpha tau, I won't write that part, and a pack of a tau 2 V2, again, as exists alpha tau. That's the full form of the value, right? Okay, these two packs are related at this type when? Think back to what you did for universal types. What did you do for universal types? For universal types, you said something like, for all alpha tau, for all alpha E1 and for all alpha E2 are related, if you give me some tau 1, tau 2, and a relation on tau 1s and tau 2s, then I take those tau 1 and tau 2 and I stick them into the bodies of my big lambdas, I get related results, right? And that relation, I go extend my row with it. Sorry to be doing that all in words. But, okay. But there was a for all tau 1, tau 2, and for all relations. Here it's going to be an exists. Because it's an exists. Right? So these two packs are related if there exists a relation R that belongs to rel of these two witness types, tau 1 and tau 2. There exists a relation R such that using that relation, these two values that are sitting inside the packs, so V1 and V2, are related. But what is the type of that V1 and V2? What type do they need to be related at? Their values, so I'm going to put value relation here. What type do they need to be related at? Tau, exactly. This tau right out here. But that tau has an alpha free in it, which we need to close. And we need to close it with the tau 1 and the tau 2 and use the relation R for it. So we're going to say it has to be related at the type tau under our original row, which we now extend with our mapping for alpha, because this guy is alpha free, so we need to provide that binding here. So alpha has to map to these two witness types, tau 1 and tau 2, and the relation R. Okay? All right. Okay, so we've done the entire value relation. I think you can imagine what the expression relation is like. Should I keep going? How much longer do I keep going? I think I'm out of time. Should I wrap up in 5 minutes? Quickly say some stuff? Keep going, okay. All right, let's do the E relation then. That's what's left. Well, and then the top level. So, again, erasing help, please, someone. That end. Don't erase compiler correctness. Oh, then there's nothing else to erase. Never mind, sorry. Okay, so the E relation, remember how whenever we define the E relation, we just say E of tau and we don't really distinguish between different cases of the types? We're going to do exactly the same here. In this case, the letter that represents all of our types is this phi over here, again. So I'm going to say the E relation at any multi-language type phi, this can be blue, it can be red. Okay? So that phi stands for every blue or red type in our language. Okay. That is equal to what? What expressions are related at this? Now again, they're going to be closed expressions. We want to make sure that they're well typed. They have type phi under closed delta, empty delta, and empty gamma. Okay, I'm not writing that part down, but it should be written down. But other than that, so we just want these to be, this is a white type, right? It's an arbitrary multi-language expression. So you need to pick an E1 and an E2. They need to be related. Now, by the way, something implicit just happened. If this phi happens to be a blue type, notice that these guys will be blue. They will be forced to be. And if this is a red type, these guys will be red. They'll be forced to be. If you just look at the grammar that we have, that's what falls out. The grammar and the typing rules. Okay, so E1 and E2 are related when? Well, when exactly what we have been doing. For all V1 such that E1 evaluates to V1, it must be the case that there exists a V2 such that E2 evaluates to V2, and V1, V2, whatever color they happen to be, it'll be the same color as whatever you start with, are related in the V relation at our type phi. Oh, and everything should have rows. Good? Okay. Oh, and I did it asymmetric. Write the conjunct in the other direction as well. Okay, it should be both directions. Should I write it? I won't write it. It needs to be both directions because we want a symmetric one. Okay. So, and yeah, other directions. Okay. Now we need to do our top-level logical relation, right? Because we want something that corresponds to contextual equivalence. So contextual equivalence needs to be between any white E1 and E2, right? I haven't even written down the definition of contextual equivalence, but it's, again, the normal one that would fall out, but this time for the multi-language. And if you want, we can write it in a minute. OK, so let's do the top-level relation here at the bottom. So this time, we have a delta. Delta is always going to be red, right? Delta and a gamma. And we want E1 to be logically related to E2 at some type phi. Again, right? The white means the colors are all going to work out properly. So first thing that we want, and maybe this part I will not write down, but you guys should write down. We want to say that under delta gamma, E1 is well-typed and has type phi. That should be my first conjunct. Then we want to say under delta gamma, E2 has type phi. Okay? As in, we're only defining the logical relation for well-typed things. And then we'll get to the interesting part. It's OK if I don't write that down, right? OK, let's get to the interesting part. What is the interesting part? Well, we don't have step indices, so we don't have to say for all k greater than or equal to 0. If you did have recursive types in your language, you would have that, right? But now all we want to do is we want to close off all the type variables, and we want to close off all the term variables. We know really well how to close off term variables. But we've never, at least in these 3 lectures, we haven't closed off type variables, right? Because we haven't done anything with type abstraction. So what I'm going to do, so effectively what we're doing is we're using row to close off any free type variables in the types, right? So here we're going to have to select a row that's a closing substitution, so to speak, for all the red alphas that appear in this type. So what we're going to say is we're going to say for all row, and I'll write it as in D of delta. Okay? And what is D of delta? Well, we'll define it inductively again. Basically, it needs to be rows. Interpretation for any alpha needs to be, so for the empty delta, it's just an empty row. It doesn't map any alphas to anything. But for one of these, it is a row extended with alpha maps to a triple of tau 1, tau 2, and r, such that rho is in D of delta, and rho is in D of delta, and our relation is a good one. Okay? What does that mean? Our relation R is a good one, means it must belong to rel. Whatever properties rel says, it should have. In our case, it only says that the values inside the relation R have to be well-typed, of type tau 1 and tau 2. Okay? All right. So now we know what we're doing when we're picking these rows. We're basically finding types and relations for all the alphas that were open. Then we are going to have to pick gammas from G gamma to close off the term variables. And here, I won't write the empty case, but, ooh. What's gamma? Red variables and blue variables, right? So gamma of empty is the empty substitution, right? Just like yesterday. Gamma of this shape, we say a substitution, little gamma, that has blue x mapped to what? We need 2 values, right? It's a binary relation. And they'll both be blue, right? V1, V2, because they have to have this blue type. Okay? Such that little gamma is in G of gamma as before, and the 2 blue V's are in V of the blue tau. Okay? And I'm not going to write the third case. There's one more case which has red x of type, red x of what type? Red x of type, sorry, translation type, right? And then you can fill that out. Two red values are related. The gamma has to be in there, and the two red values have to be related at the type tau plus.
You also need to be passing through your row.
You need to be passing through your row. See, I carefully put it. Oh, I didn't put it over there. You're right. You need to be passing through row to this relation because the V relation requires it. Okay? And here I need to pass it here as well. Thank you. Okay, so now that we have all that, we can close things off. And I'm going to, again, adopt the convention that I've been adopting, right? I always write little gamma 1 to say get all the values on the left, little gamma 2 to say get all the values on the right. I'm going to do the same thing with row. Row 1 means get all the tau 1s. Row 2, right, these tau 1s. Row 2 means get all the tau 2s and use them to close off the free type variables that appear in these terms. Okay? So row 1, gamma 1 of E1, I hope you can see, is related to row 2 of gamma 2 of E2 in the E relation at our type phi with row passed along. Okay? All right. So that's pretty standard. There's nothing terribly odd that happens there. Okay, so then what do we do? Well, let's wrap up. We have a logical relation. We have to prove the fundamental property for this logical relation, right? So for every single typing rule in your multi-language semantics, it means you're going to have all those source typing rules pulled in, all the target language typing rules, and the two boundary rules. For every single one of those typing rules, you're going to prove that the terms are logically related, right? That's the fundamental property, just like we have been doing. So you prove the fundamental property. You then prove that this logical relation is sound and complete with respect to contextual equivalence. There's actually one condition that I haven't put on the board, which you need for completeness, but I'm not going to go into it, I think. We need like one extra condition in rel in order to get that this logical relation is complete with respect to contextual equivalence. Watch my lectures from last year and you'll see. Okay, these R's need to be what we call equivalence respecting. So if V1, V2 are in there, and then you have another V1 prime and V2 prime such that these guys are equivalent to those, then that V1 prime and V2 prime need to be in there too. You need that for a base case. Again, watch previous lectures and it spells it all out. Okay, so you prove your logical relation is sound and complete with respect to contextual equivalence of the multi-language, and then you use the logical relation to prove the compiler correctness theorem. All right? In the middle, a couple of interesting things that happen is that in order to prove the fundamental property, you will have to prove something called a bridge lemma. The bridge lemma basically says that if you have two blue E's related at a blue type in the E relation, then those two blue E's with TS wrappers around them are in, you want me to write it down? If you have two blue E's, E1 and E2, that belong to E of a blue type, then those same two blue E's, with wrappers around them, have to be related in E of the translated type. This is something that someone asked about, the bridge lemma. You asked about. And then vice versa. So if two red E's are related, then the wrapped versions of those, if two red E's are related at type tau plus, then the wrapped versions of those are related at type tau. And you have to prove both of these bridge lemmas simultaneously because they refer to each other. Because remember in the function case, you go back and forth. That's why you have to prove them simultaneously. And it's all by induction on the type tau, the source type tau. And then once you're done with that, your fundamental property is proved. But before you start proving compiler correctness, you have to prove that boundary cancellation property that I talked about on a slide earlier. Okay? Because that becomes essential while you're carrying out your compiler correctness proofs. Often you just need to cancel out boundaries because they pile up. All right? Okay, so that's sort of the whole big picture. Let me just see. What else do I want to say? Any questions? Any final questions? Yes?
What are the tree ones or row ones? Can you come from there?
Here? So the row 1 is my shorthand for saying that if you have a row that maps alphas to tau 1, tau 2s, and r's, turn that into a substitution that maps an alpha to a tau 1. Extract all the alpha tau 1 bindings and apply that as a substitution so that you can go in and all of the free alphas that you have in E1, you can close them off with those tau 1s. And similarly, row 2 means close them off with the tau 2s that are in the triple.
So they're like some sort of projection out of
They're projection out of these triples that our rows are. Okay. Projection was the right word that I should have said. Okay. Anything else? Okay, I think it's time to conclude. Basically, what I wanted you to get out of this, I hope that the theme of the 4 lectures put together, is that, once you sort of learn the basics of logical relations, that it's easy to sort of look at your context, hopefully easy now, to look at your context and figure out how to do things right for this particular application, right? That was the point of showing you different kinds of situations and sort of asking the question of, hey, what do we need to do here, right, given what we're trying to accomplish. One other thing to say is that this compiler correctness theorem, even though I've put the boundary on this side, once you have boundary cancellation, you get a corollary, which says, put another boundary out here, it cancels out, and that's equivalent to Ts of E is contextually equivalent to just the red E, right? Both theorems, both ways of even stating compiler correctness are absolutely equivalent. Okay? All right. That's it. Thank you.
On behalf of all the students at OPLSS, I'd like to thank Professor Ahmed for mechanically relating logical relations for colorful compiler correctness.
Especially like the conversations that I've had with you guys. If anyone is interested in any of this, please do send me a mail. All right?